welcome to the course on 3G, 4G wireless communication systems. So, in the last lecture we were looking at the final advantage or one of the advantage of CDMA communication systems, that is code division multiple access based communication systems, and we concluded an analysis regarding the rake receiver, where we said that CDMA can be advantageously employed to coherently combine the multipath components to now extract multipath diversity. Hence, the SNR at the receiver, at the rake receiver, is norm h square times PO P naught by sigma n square, where this norm h square, remember this is similar to the Maxwell ratio combining, and it represents the diversity of the rake receiver. Hence, another big advantage and a very significant advantage in CDMA systems is that they enable extraction of multipath diversity, which was not previously possible in the kind of systems that we looked at, and this is possible through the rake receiver. Hence, rake receiver has a significant role in CDMA based communication systems. With that, we moved on to the analysis of the downlink of a CDMA based communication system. We said in the downlink there is a base station, it is communicating with several users. However, in CDMA they are not differentiated on time or frequency, but they are differentiated on the basis of the codes. So, we have the following model where each user signal SI is multiplied with the user's code CI. All these signals are put together and transmitted on the downlink. So, the net transmitted signal is nothing but symbol multiplied by code, some signals of all users, and then transmitted on the downlink. That is the system model we looked at, and then we passed it to a frequency selective channel. We said a frequency selective channel is characterized by channel taps H0, 0, H01, H0, L minus 1. This is like an L tap filter. This is similar to what we had seen in the case of a rake receiver. And finally, we said that the received signal model is given by this expression that we have seen here. Now, remember, each user signal passes through this L tap frequency selective channel, and there are k plus 1 users, that is 0 which is the desired, who is the desired user, and 1 to k who are the interfering users. So, there are k plus 1 users passing through an L component frequency channels. Hence, there are totally at the received output there are k plus 1 times L components. Out of these k plus 1 times L components belong to the user 0, and the remaining k L components belong to the interfering users. This is the point at which we had stopped in the last lecture. Now, let us resume our analysis of the CDMA downlink. So, now let us start with this expression that we have over here, which is the received signal. I am looking at the received downlink CDMA signal after received downlink CDMA signal after decorrelation, that is D equals 0 to L minus 1. Remember, we had correlated this with the code sequence corresponding to user 0. So, let me resume with that analysis, that is D equals 0 to L minus 1 summation k equals 0 to k minus 1 summation m equals 0 to n minus 1 H0 d times Sk times Ck m minus d times C naught of m. This is the summation over the number of chips. This is the summation over the number of users, and this is the summation over the number of paths, that is 0 to L minus 1. Now, I will separate this, as we said, into different components. First, I am correlating with the chip sequence of user 0 corresponding to a lag of 0. So, first let me extract the component corresponding to user 0 at lag 0. So, the component corresponding to user 0, so component corresponding to user 0 path 0, that is the first component. Then I have L minus 1 components corresponding to user 0 and the other L minus 1 paths, plus the other L minus 1 components are L minus 1 components of user 0 corresponding to the other L minus 1 paths. This is similar to the rake receiver. We are in rake receiver we are correlating with C0 M that extracts the path corresponding to 0 lag. The rest of the paths form the interference, plus now there are also, remember, there is also multi user interference, hence there are plus KL components corresponding to the multipath components of the interfering users. All right. So, I will write this summation, which is the next net received signal, as the sum of these three components, which can be represented as 1 over n, m equals 0 to n minus 1, that is summation over all chips h 0 0 s 0 c 0 m c 0 m. This is the component corresponding to user 0 path 0, that is path with lag 0, plus, so let me write this as user 0 path 0 plus the next L minus 1 components corresponding to user 0 and the other L minus 1 paths. This I will write as summation d equals 1 to L minus 1, m equals 0 to n minus 1, s 0 symbol of user 0, h 0 of d, that is the channel coefficient corresponding to the dth lag, C 0 of m minus d times C 0 of m. Remember, this summation goes from d equals 1 to L minus 1, that is it is going from the first path to the L minus 1th path, that is all paths other than the 0th path, but for user 0. Hence, these are L minus 1 multipath components of user 0, plus now I will write the KL components of the interfering users, that will be summation 1 over n. Now, I will sum over the number of users, k equals 1 to capital K, summation d equals 0 to L minus 1, summation m equals 0 to n minus 1, sk h 0 d ck m minus d c 0 of m. This is nothing but the KL components of the interfering users. Look at this, we only have users from k equals 1 to k, that is all users other than the 0th user, who is the desired user that we are considering. Hence, this is the multi user interface. This is from users 1 up to capital K, and this is also the multi user interference. Now, in this let us look at the first component, that is the component corresponding to path 0 of user 0 who is the desired user. So, let me first look at this first component. I will write this over here, that is desired user zeroth path, and that is simply 1 over n summation m equals 0 to n minus 1 h 0 0 s 0 c 0 of m into c 0 of m, that is correlating user 0 zeroth path with code shifted by 0. So, c 0 m into c 0 m, that is c 0 m square. Remember, c 0 m is either plus or minus 1. In either case, c 0 square of m is 1, this we have seen many times, that is the self correlation of a sequence. Hence, this is simply going to be 1 over n summation m equals 0 to n minus 1 h 0 0 into s 0 into c 0 m square is 1. This is simply nothing but h 0 0 into s 0 summed n times, which is n over n, which is nothing but h 0 0 s of 0. All right. So, the first component, as in the rake receiver, the correlation with c 0 m, which corresponds to a lag of 0, extracts the 0th path of the desired user, and that is what we are observing. It is nothing but symbol 0 of the user 0 multiplied by the channel coefficient h 0 0, which is the channel coefficient corresponding to the 0th path. Now, let us look at what happens to the rest of the component. If you go back here, I want to start looking at what about the rest of the components, that is there are L minus 1 multipath components of user 0. What about these components? So, let us look at the multipath interference of user 0. So, I will call this multipath interference or MPI. Just like MUI is multi-user interference, MPI is multi-path interference. And how does the multi-path interference look? The multi-path interference looks as follows, that is summation 1 over n d equals 1 to L minus 1, that is all the L minus 1 paths other than the 0th path, summation m equals 0 to n minus 1, that is over the chips, h 0 of d c 0 m minus d c 0 of m times the symbol s 0. Remember, s 0 is common, so I will take out s 0. So, this is 1 over n s 0. Summation d equals 1 to L minus 1 h 0 of d, the rest is c 0 m minus d correlated with c 0 m divided by n. This is nothing but the self correlation with a lag d. Remember, we have a notation for this, this is nothing but r 0 0 of d, and let me remind you, r 0 of d is random variable of mean 0 and variance 1 over n. All right. So, this is in fact noise, this multipath interference is an interference noise, all right, and which the variance of this we will compute shortly. So, expected. So, if we look at this multipath interference, what is, let us compute what is the power or what is the power of this multipath interference. Let us compute, let me denote this as MPI. Now, expected MPI is nothing but expected of this expression above, which is expected 1 over n summation S 0 summation d equals 1 to L minus 1 h 0 of d or 0 0 of d Now, I can take the expectation operator inside and I can write it as the sum of the expectation of each of the individual terms, and that is simply nothing but 1 over n S0 summation d equals 1 to L minus 1 H0 of d into expected R00 of d, but we know expected R00 of d, this is 0, hence this is the sum of L minus 1 terms, each of which is 0, hence this is 0. Hence we can say the expected value of this multipath interference is 0. Similarly, what is the variance of this multipath interference? The variance of this multipath interference what is the variance of this multipath interference? Variance of this multipath interference is nothing but expected MPI square, which is nothing but expected of square of this term, which is expected of 1 over n S0 summation d equals 1 to L minus 1 H0 of d times R00 of d whole square. This is nothing but 1 over n square expected S0 square, that is expected symbol square, but this is nothing but the power in user 0 times expected summation d equals 1 to L minus 1 H0 d whole square into expected R00 d square. Alright, so the variance of this is nothing but expected 1 over n square expected S0 square, which is nothing but the power of user 0 times summed over all the L minus 1 multipath components H0 d square, that is the power in the dth component, times expected R00 d, which is the self correlation square. We know this self correlation, expected self correlation is nothing but expected, this is nothing, this 1 over n square times this is nothing but 1 over n. Hence, this gives, this is nothing but equal to P0, the power of user 0, times summation d equals 1 to L minus 1 H0 d square summation into 1 over n. So, I will write this as P0 over n summation d equals 1 to L minus 1 H0 d whole square. Alright, so, this is the expression for the multipath. So, the power in the multipath interference, that is, this is the expression for the power in the multipath interference corresponding to the L minus 1 components, L minus 1 interfering components that interfering with the component corresponding to the path 0, that is the path with delay 0. Alright. And just to simplify this a little bit more analytically, this is contains all the L minus 1 components. I will also add, just to make it symmetrical, I will also add the 0th component and subtract the 0th component. So, this can be written just mathematically as this can be written as P0 over n summation d equals 0 to L minus 1 H0 d whole square minus P0 over n H0 square. remember I am adding, there was no component d equals 0 in the previous expression, I am adding the d equals 0 component, I am subtracting the d equals 0 component. This help me write P 0 over n norm of h naught square minus P 0 over n magnitude of h 0 square, where norm of h naught square, where this quantity norm of h naught square is nothing but the total received power in the channel, that is the sum of the magnitude squares of the individual channel components, that is magnitude h 0 square plus magnitude h 0 1 square plus magnitude h 0 L minus 1 square. All right. So, this is the interference power corresponding to the multipath interference, which consists of the L minus 1 components of the same user. So, this is the interference similar to the rake receiver, this is the interference similar to the rake receiver which interfere with the desired component of the desired user. Remember, in the rake receiver we had ignored this component, we said this is approximately equal to 0, but now for the sake of completeness we are deriving this expression more thoroughly. So, this acts as interference and the power in the interference is nothing but the power of the user. However, there is a factor of n, this is related to the spreading gain in the CDMA system, remember, times the norm of the channel minus P 0 n norm h 0 square. This is just, this last step is just to make the expression more symmetrical. All right. So, this last step is just to make the expression a little more simpler to handle and make it a little more structured, otherwise there is no real significance of this last step. Now comes something even more interesting, which is how do you handle the multi user interference. So, now remember we still have the KL components corresponding to the K interfering users passing through the L tap multipath channel. So, now we have to handle the KL components of multi user interference or MUI, and those components can be expressed as follows. Those components can be expressed as the multi user interference is nothing but the MUI equals 1 over n sigma summation k small k equals 1 to capital K summation over all paths d equals 0 to L minus 1 paths, that is the L paths of the interfering user, summation over number of chips, that is m equal to 0 to n minus 1 Sk. Remember, now you have the symbol of the kth user Sk, h 0 of d, c 0 of m, ck of m minus d. This can be written as summation over all users k equals 1 to capital K, summation over all paths d equals 0 to L minus 1. I will move this 1 over n inside, and this is nothing but Sk h 0 of d, and this c 0 m ck m minus d summation over L is nothing but the cross correlation between the code sequences of user 0 and user k. Hence, I will write this as 0 k with lag of d. All right. So, this is essentially the multi user interface. This is the MUI term, or this is the multi user interference term in the CDMA system. As we did previously, again let us compute the expected value of this multi user interference. The expected value of this multi user interference, again it is very simple, it is nothing but if you go here, that is the sum of the expected values of each component, but each component has R 0 k d, each expected value of each of this is 0. So, the net expected value is again 0, that is the mean is 0. No harm in writing this down, let us just write this down. So, this is summation k equals 1 to capital K summation d equals 0 to L minus 1 H 0 of d S k expected R 0 k of d, expected each R 0 k of d is 0, hence this is summation of zeros, hence this is 0. So, this is interference with expected value 0, and that we have seen this several times before. So, there is no need to again belabor that point. So, this expected value is 0. What is more interesting is the power of this component, or what is the variance of this component, that will give us the power of the interference. So, if I look at expected MUI square, which is nothing but the power in the multi-user interference. This is the power in the multi-user interference. Now, why are we computing the power in the interference? Remember, the interference acts similar to noise. So, we want to know what is the signal to noise plus interference ratio. We want to know now, not only because the signal is degraded not only by the noise power, but it also degraded by the interference. Hence, now a more relevant term to consider in CDMA is what is known as SINR, that is not SNR, which is the signal to noise ratio, but SINR, which is the signal to interference plus noise ratio. That is what we are trying to do here. We are trying to characterize the SINR of this system, and these are all steps that lead us towards that. That is a thorough analysis of the SINR of the system. And the expected multi-user interference square, which is the power in the multi-user interference, is nothing but summation k equals 1 to capital K summation d equals 0 to L minus 1 expected Sk square or expected Sk square times magnitude H 0 d square into expected R 0 k d square. This we have seen before, expected R 0 k, cross correlation between 0 and kth small k user for shifted lag d is nothing but 1 over n. Hence, this I will write as 1 over n summation k equals 1 to capital K summation d equals 0 to L minus 1 magnitude H 0 d square into expected S square square is nothing but P k. And remember, this can be written as, since this does not depend on d, I will pull this out of the summation. Sorry, there is no 1 over there is 1 over n. This is nothing but 1 over n summation k equals 1 to capital K P k summation d equals 0 to L minus 1 magnitude H 0 d whole square. This is nothing but, this is very simple. Now, summation d equals 0 to L minus 1 magnitude H 0 d whole square is nothing but the norm of the channel. Hence, this is nothing but 1 over n norm of the channel vector H square times summation P k, k equals 1 to capital K over n. So, what is the significance of this expression? First, what is this expression? This expression is the power, interference power in the L minus in the KL components corresponding to the multi-user interference. The other thing is, hence this is the power in the channel times the power of all the interfering users, that is k equals 1 to capital K, those are the interfering users, times 1 over n. Look at this, there is still a factor of 1 over n, which is very important, which is nothing but the spreading gain of this system. If this 1 over n is not there, then this is a huge interference power which cannot be handled, alright. It is this 1 over n, as is always there in a CDMA system, which makes this power go to 0 as spreading length increases. makes this multi-user interference manageable. So, because you are not transmitting on the same time, because you are transmitting on the same time and same frequency, these signals of each user are interfering with each other. However, because of the ingenuity in designing these random codes or this random looking spreading codes, this interference is suppressed by a factor of n. Now, we put all these things together to analyze the system. So, the total interference, first let me write the total interference is MPI plus MUI. So, total interference equals MPI plus MUI. So, total interference power is MPI power plus MUI power, which is nothing but summation 1 over n k equals 0. Now, remember there is also multipath interference coming from other components of user 0. So, this is k equals 0 to capital K summation p k into norm h 0 square minus 1 over n p 0 h 0 magnitude square, plus if I want to look at total interference plus noise, let me also add noise to this MPI plus MUI plus noise, and we know noise is nothing but sigma n square divided by n. Hence, this is the total interference power. However, remember there is a catch here, this is the total interference plus noise power corresponding to only decorrelating with C0 of m. This is one of the components of the rake receiver. Now, when you decorrelate with C0 m minus 1 similar to the rake receiver to extract the path at delay 1, you will have interference, you will have similar interference when you decorrelate with C0 m minus 2, so on until C0 m minus L minus 1. So, you will have L such interference terms. So, now the system model we have, remember going back, the signal is here, that is still H0 S0 corresponding to extracting the 0th component. So, finally, after you extract the 0th component, the 0th component looks like R 0 equals H 0 0 S 0 plus W 0. This is the noise plus interference component. R 1 equals H 0 of 1, that is the channel coefficient of user 0 corresponding to lag 1 times S 0 plus W 1, that is noise and interference corresponding to the second decorrelation with C 0 m minus 1. R 2 is H 0 2 S 0 plus W 2 corresponding to decorrelation with C 0 m minus 2, so on so forth. This is R of L minus 1, which is equal to H 0 L minus 1 S 0 plus W L minus 1. This is after decorrelating with C 0 m minus each delay. Alright, so there are L components, so you will have L components corresponding to the L decorrelations, and this we have seen this before. This is fairly similar, in fact I would say exactly similar to what we have seen in the case of rake receiver, except for these W's, which are now not simply noise, but they are noise plus interference. So, otherwise this is exactly similar to what we have seen in the rake receiver. However, we had to do this analysis, which is a slightly involved analysis, I would say. I know it is fairly messy. If you go back and look at the expressions, the analysis is slightly rigorous and messy, but in the case of CDMA, this has to be done. There is no other way to get around it, to give the complete import of a CDMA system, which is essentially a very rich system in which different users, different multipath components are all interfering with each other, yet you can make sense of the received signal at the receiver simply because of that they are transmitted on different codes, which are essentially correspond to a signature. This corresponds to this, it is like a user signing his information, with his signature. So, these codes over the air are nothing but correspond to the signatures of the different users over a CDMA channel. So, now I take these different components and we know what to do now. It is similar to what we do in a Maxwell ratio combining or the rake combining, coherently combine these different components to extract, to finally get the received statistic, to decode the symbol. So, I will combine them as follows: conjugate 0 divided by norm h times r of 0 plus h naught 1 conjugate divided by norm h into r of 1 plus h naught conjugate L minus 1 divided by norm h into r of L minus 1. Remember, this is similar to rake receiver. The signal is h naught 0 into s 0 s 0. So, I am multiplying this by h conjugate 0 divided by norm h. This one is h 0 1 into s 0. So, I am multiplying this by h conjugate 1 divided by norm of h, multiplying this by conjugates, adding them up across all branches of the rake receiver, and this is nothing but coherent combining across the branches. This, so now this has two components. Let us first look at the signal component. So, when I combine this coherently, I will have a signal component, I will have a noise component. So, the signal component is nothing but, so let me look at the signal . The signal component is nothing but, or let me write this as the signal is nothing but magnitude or h 0 conjugate divided by norm h into h 0 0 s 0 plus h 0 conjugate 1 divided by magnitude h into h 0 1 into s 0 plus so on, as we said, h 0 conjugate L minus 1 divided by magnitude of h into h 0 of L minus 1 into s 0. This is nothing but magnitude h 0 0 square divided by magnitude h times s 0 plus magnitude h 0 1 square divided by norm h times s 0 plus so on magnitude h or magnitude h 0 of L minus 1 square divided by magnitude h into s 0. This is nothing but sum of all these components, but sum of all these components is nothing but magnitude h 0 square divided by magnitude h 0 into s 0. This is nothing but magnitude h 0 into s 0. Hence, the power is nothing but magnitude h norm of h 0 square times. So, the power in signal is nothing but expected magnitude h 0 times s of 0, that is what we already seen before. This is norm h 0 square times expected s 0 square, that is norm h 0 square times p of 0, that is the power times the power in the channel. This is what we have seen many times before. This is what we have seen in the case of Maxwell ratio combiner, in the case of rake receiver and so on. This is nothing but you coherently combining. So, you are extracting the power multiplied by the total power in the channel, that is the meaning of coherent combination combining. So, it is power in the user 0 times the magnitude of the channel square. How about the noise power? The noise power is something more interesting. Let us look at the ith branch. Let us look at the ith branch. The ith branch is being combined by h 0 I conjugate divided by norm of H 0 times into W I, this is noise plus interference power. Hence, the variance of this ith branch sigma W I square is nothing but power in this, that is expected H 0 I conjugate divided by magnitude H 0 magnitude square times expected W I square, which is nothing but, or expected magnitude W I square, which is nothing but the power in the noise. This is nothing but, because the expression is slightly tricky, this is nothing but magnitude of H naught conjugate I is nothing but magnitude of H naught of I, this is nothing but magnitude H naught of I square divided by magnitude H naught square. And remember, we computed an expression for the multipath plus multi-user interference. I will write that expression over here. We computed it for the path 0 of user 0, but I can extend it to path I of user 0. It is the same expression, instead of H naught I will have H naught of 0, I will have H naught of I. So, that expression is nothing but 1 over n times summation k equals 0 to capital K P K norm H square minus 1 over n P naught magnitude H naught of I whole square plus sigma n squared over n. All right. So, this is the expression for the interference caused, this is the expression for the interference after weighing by the weight corresponding to the ith branch. Let me just write this down as follows. Let me further simplify it. Remember, as I said, the simplifications are fairly strenuous. So, I urge you to remain with me on this, and you can sit down again. You need to sit down and actually verify some of these expressions, because the expressions in the CDMA are not very straightforward, and if you want to completely characterize this thing, because it is a rich system, you have to write down some of these laborious expressions. That is nothing but, look at this in here, the norm H square, the norm H naught squares, they cancel. So, finally, what you can write this as, which is simplified as this is k equals 0 to capital K summation P k magnitude H naught of I square minus 1 over n P naught magnitude H naught I square divided by norm H naught square plus sigma n square over n times magnitude H naught I square divided by norm H naught square. Alright, so this is the net expression that we have for the interference on the ith branch. So, the total interference is nothing but now the sum of the interference across all these ith branch. So, total interference after recombining is the sum of the interference across all these branches, and that is nothing but 1 over n k equals 0 summation amongst all users, summation on all paths H naught I square. So, that gives me 1 over n summation k equals 0 to capital K P k times summation over all paths, that gives me nothing but magnitude H 0 square minus P 0 over n divided by into I equals 0 to L minus 1 magnitude of, it should be a power of 4 over here, this is magnitude of HOI to the power 4 divided by magnitude H0 square plus summation sigma n squared over a n, summation H naught of I magnitude square is nothing but magnitude H naught square divided by magnitude H naught square, both of these cancel. So, you will get, when you sum across all branches, you will get sigma n squared over n, and let me highlight this again. This is the total multipath interference plus multi-user interference plus noise. So, this is not a simple derivation by any means, it is fairly rigorous and fairly strenuous. So, there might also have been some minor errors that might have crept in, but typographical errors, I apologize for that, because there are so many terms here, it is difficult to keep track of some of these at some point. But essentially I think the central idea in this is clear. The central idea is CDMA is a rich system. So, there is multipath interference as well as multi-user interference plus thermal noise, that is always there. So, hence look at this component, this has the powers of all users including user 0. The strange thing about this interference, look at this, this is summation k equals 0 to k, that is summation of powers of all users, even the desired user P0 is interfering with himself. Why? Because when you are extracting one component corresponding to a path, the rest of the paths are interfering with this component. So, it is a very interesting expression in which there is a lot of interference, hence this is a rich system. But now we have characterized the power in the interference, and of course, as you see there is a 1 over n in the denominator of each of these terms, which means the interference grows progressively to 0 as the spreading gain increases or the code length increases. That is the essential idea. So, I will write the final multi-user CDMA downlink SNR. So, finally, thanks to all the manipulations we have done, we can now write SINR. Remember, we defined SINR as signal to interference plus noise, that is signal to interference plus noise ratio, or the signal power to interference power plus noise power ratio. SINR is nothing but norm H naught square P 0 into n, this is the spreading gain, divided by summation k equals 0 to capital K magnitude H naught square minus P naught summation P k, sorry, summation P k equals 0 to K magnitude H naught square minus P naught summation I equals 0 to L minus 1 H naught I magnitude to the power of 4 divided by magnitude H naught square plus sigma n square. Right, this is the complete expression for the multi-user CDMA downlink signal to interference plus noise ratio. Remember, let me just point out where we started from. We started from this scenario here, where there is a base station. The base station is multiplying the signal corresponding to each user, S0 with code 0, S1 with code 1, S so on and so forth, Sk with code k, combining this and transmitting that aggregate signal on the downlink, and then we started looking at how do you process the received signal at user 0, who is the desired user 0. No particular favor to user 0, it is just that as an example we started we considered user 0 as the desired user, and we can similarly repeat it at each other user, the expression is going to be symmetrical. And finally, what we have arrived at here in this expression over here is the complete, the actual multi-user, the actual SNR, SINR of the desired user, taking into account, not neglecting anything. In fact, this is not an approximation, this is in fact an exact expression where we have considered the multipath interference, the multi-user interference and the thermal noise at the receiver. So, this is a thorough expression and it is fairly strenuous, but remember, couple of key observations. First, there is the spreading gain, which is the factor of n, and moreover all other users including the desired user interfere with himself. All other users, naturally, because you are transmitting the aggregate signal, the desired user himself, because when you extract one path, the rest of the paths interfere with this path. Hence, this is a very interesting expression. And let me point out one final thing. If you want to increase the SINR of this by pumping more power P naught into the desired user, that can have repercussions, because as the desired power increases in the numerator, look at this, in the denominator also there is a P0, because the rest of the paths are interfering with a desired path. So, that increases both signal power and that increases also interference power. This is not something that we have seen before. So, this is something that is strange, and this is something that is the cornerstone in wireless communications, which is especially CDMA, because of the rich interference. When you increase the power, the interference also increases. So, it is a fairly strange phenomenon, and this results in fact in CDMA, it results in what is known as flattening out of the bit error rate curves, because after some point, as you are increasing the power, the interference is also increasing, which means you cannot improve your signal to interference and noise ratio beyond a certain limit. Anyway, that is some auxiliary information. If you don't fully appreciate it, that is fine, but this is the final expression for the downlink SINR at the desired user 0. Thank you very much for your extra patience while deriving this expression. The next class we will continue with the uplink, but that will be fairly straightforward given our knowledge and intuition regarding this. Thank you.